Hi, I'm Olga, and I'm going to present our work in progress on subword geometry, which is a new approach for classifying languages. Language classification has become an important topic in the modern NLP, especially since there are many people aiming at producing language-agnostic and multilingual models, and since the widespread use of the language transfer technique. The typical solution for language sampling for such tasks is to use language databases, for example, WALS, World Atlas of Language Structures. However, if we aim at producing highly multilingual models and using massive language corpora, we will notice that many languages are not present in WALS. For example, in the case of JW300, around 2/3 of languages are not there. And many others are not comparable. For example, these two languages, they have very few features listed, and we cannot really compare them to each other. So what we can do in such a situation? There are some solutions available, such as measuring text entropy. However, it's not enough for deeper linguistic analysis. We propose a solution that goes deeper than text entropy. This is based on subword properties, and it is able to capture both universals and fine-grained differences. The main concept that we introduce is word shapes. Word shapes are sequences of subwords lengths, and they can be even or uneven. On this example, there are 3 English words segmented by the byte pair encoding algorithm, and on top of each of the segments, there is its length written. So if we imagine this sequence of segment lengths marked on a wire, and if we want to create a geometric figure out of it, we will see that the first one will be open and uneven, the second one will be even, and the third one would be somewhere in between. We can quantify this property by introducing a measure for describing word shapes. We call this measure the Unevenness Index, and we calculate it as follows. We find the maximum and the minimum segment lengths for a given token, and we subtract them from each other. Despite the simplicity of this measure, it is highly correlated with variance, but it's easier in computation. The lower unevenness index values indicate the even word shapes, and the higher it gets, the more uneven the shape becomes. For the previous example, we can see that for the first figure, the unevenness index value is equal to 6, the second unevenness index equals 0, and the third one is 2. For our experiments, we use the corpus that we build ourselves. It's called 100LC, and it will be publicly available soon. It is based on 100 language sample described in WALS. Our corpus comprises texts in different genres, and for the experiments, we filter all the languages that have more than 10,000 tokens. First, we tokenize our raw data by using the polyglot tool, then we segment by using BPE, we calculate word shapes and the unevenness index, and then we quantify the index distribution properties. Now let's have a look at the results. Here on the plot, we can see the word length on the x-axis and the unevenness index on the y-axis. The size of the points indicate the frequency of the unevenness index for the given word length. Now, since unevenness index is dependent on word length and it cannot exceed word length -2 for a given word length, we will always see this left diagonal. Now let's have a look at all 41 language plots, and we can notice that the most frequent points are always situated in the same place, which is a lower part on the left. That means that shorter words with even shapes are most frequent cross-linguistically. The differences in these plots are mostly in that how dispersed are the points in space and where exactly do they tend to group. It's either in the bottom of the plot or in other different places. Now we can quantify these differences as well. So first way of quantification that we suggest is to look at the surface area. The surface area quantifies how many points are filled in the combinatorial space that could have been filled. Now, In these two examples, on the left side there is Alanblak. That's a language spoken in Papua New Guinea. On the right side there is Chukchi, the language spoken in Russia. Both of these languages are polysynthetic and their entropy values are quite similar to each other. However, we can see that according to our analysis, these languages behave differently. So on the left side, we can see that Alanblak takes almost all of the points that are in this combinatorial space. In case of Chukchi, many points remain unfilled. Another measure that we suggest is called upper angle, and it reflects the preference for shapes in longer words. First, we identify the most populated regions. Those are density regions. And then we fit two diagonals. The left diagonal is always fixed, and the right one is fit according to the outline of this density region. On the plots, we can see that the angle in Chukchi plot is much more obtuse than in the Alanblak plot. That means that in Chukchi there is a clear preference towards even shapes in longer words, and in Alanblak there is no such preference. When we obtain all the values for all the languages, we can see how they relate to each other. On this plot, the surface area is on the x-axis, and the values for the upper angle are on the y-axis. We propose to split this space into 9 groups, 9 sectors, and to analyze the language groups by low, medium, and high values for area and angle. We can see from the first glance that the groups that are here, they are not typical groups that we would see in word entropy, for example. And indeed, if we color languages by their entropy value, low or high, we can see that there is little to no correlation between our measures and text entropy, which means that our approach shows indeed something different than what entropy does. Now, coming back to our two examples of Alanblak and Chukchi, we can now locate them to their respective group. So Alanblak ends up in high area mid-angle group, meaning that there are many combinations filled and that there is no shapes preference in longer words. Chukchi ends up here in mid-area high-angle group, where there are 30% of combinations filled, and that there is a clear preference towards even shapes in longer words. Now let's have a look at two more sectors in detail. This sector is low area high angle, and all the languages here, their index distribution is dispersed, and there is a preference for even shapes in longer words. Now, if we look at the plot of Russian, we can see that it's quite noisy, but despite the noise, there seems to be a pressure towards even shapes. Another extreme sector here is high area low angle sector, and the index distribution here is characterized by being dense and by the preference for uneven shapes in longer words. There are 5 languages in this sector, and there seems to be a different pressure. Now it's more of a pressure on word length, but more freedom in word shapes. So we don't see there any noise now, but we also don't see a preference towards even shapes when the words get longer. There seems to be indeed a trade-off between these two dimensions. We find a moderate negative correlation between them. We also notice that there is one sector that is not filled at all, so low area and low angle do not occur together in our experiments. Another extreme sector of high area, high angle, we can see there that the languages occur towards the edge, so this seems to be a very rare combination as well. This is the first step towards analyzing the values that we obtained, and in the future we are going to explain all these groups in detail. For now, we contribute the new method for classifying languages, which is purely data-driven, which goes deeper than text entropy, and which is based on subword length properties. We found out that shorter words with even shapes are most frequent cross-linguistically, and that languages differ in that how many word shapes are allowed, and by their preferences for shapes in longer words. Thanks for your attention.